Suppose that we are given the equation y minus x to the third equals to 1, and we want to be able to find the derivative of y. All that we have to do is to take y and to isolate it. In other words, express y explicitly in terms of x to the third plus 1. Now that we have that, we just take the derivative of y, a simple use of our rules of differentiation, and we find that y prime is equal to 3x squared. Very simple task. Suppose that instead we are presented with the equation x squared plus y squared equals to 1. You may recognize that this equation defines a circle. In fact, a circle whose radius is 1. You end up getting something like that. Okay, you can see the circle right here. This is 1, -1, 1, and -1. All of a sudden, this circle is not the graph of a function. So it is impossible to be able to find one simple expression in terms of x that will give you every single point on the circle. You will not be able to find a single one. What you can do, however, is to divide the circle or split the circle in half, in which case you have the upper semicircle and the lower semicircle. And for each of these semicircles, it is now possible to find a function or an expression in terms of x. For example, for the upper semicircle, we can think of this piece being expressed by f of x equals to the square root of 1 minus x squared. And for this other piece right here, let me use a different variable. G of x equals to negative square root of 1 minus x squared. So now I do have right here the graph of a function. This is the graph of a function with its own expression in terms of x, and I have another function right here with its own expression in terms of x. And if I want to be able, let's say, to pick a point on the circle, imagine drawing the tangent line, and I want to find the slope of the tangent line, all that I have to do is to take this particular function, apply the chain rule, and I can have the derivative. I can have the slope of the tangent line. Same thing over here. If I pick any point on the circle, draw the tangent line, I should be able to find the slope of that tangent line by now using this function right here. So far, so good. Doesn't seem like a very tedious thing to do. And you want to notice that each particular expression satisfies the original relation right here. For example, if I take x squared and I substitute the expression for the upper semicircle, I get that this is equal to x squared plus 1 minus x squared, which cancels the x squares, and I end up getting 1. So I get that the left side is equal to the right side. And the same thing happens if I now choose g of x and I substitute it here. We look at this particular, you now take this particular equation right here. The graph of this equation is represented by this curve that you see on the right. This curve is not the graph of a. Now, suppose that we're given this relation right here on the left. The graph of that relation is this graph here on the right side that looks like a little loop right here. What happens with this particular curve is that this curve is not the graph of a function. If you notice, it fails the vertical line test in this particular region. That means that we're not going to be able to find a single expression in terms of x that will give us every single point on that curve. It's just going to be impossible. So then what we can do is to choose pieces of the graph that are functions. So this piece right here is a function. This one over here is again the graph of a function, and this is a function. When you put all three pieces together, notice how you get the entire loop right here. The issue with that is that now if we want to be able to find derivatives at these points or here, we would have to find the actual expression in terms of x of these p's, and this one right here. And sometimes that can be a daunting task to do algebraically. You may have to use a computer in order to be able to do it easily. And sometimes for some more complicated curves, it is almost impossible to find every single function that represents every single piece of the curve. But then that it doesn't seem right that if I pick a point on the graph and I draw the tangent line, it doesn't feel right as if I say, well, I'm not going to be able to find the slope of the tangent line. I should still be able to find the slope of this tangent line given a point on the graph. Even if I choose another one over here, I should still be able to find the slope of the tangent line. And this is really the good news. And this is the benefit of implicit differentiation. Implicit differentiation will say, well, yeah, we cannot find every single expression for all the pieces. It may not be feasible, or it may be too difficult to find those expressions to differentiate, but we should still be able to pick a point on the curve and think of the tangent line passing through that point and be able to generate or calculate the slope of that tangent line. We should still be able to do that even if we don't have every single equation for every piece that is a function on that curve. And that's what I want to do now. I want to be able to show you how to put into practice the whole idea behind differentiating implicitly. Here I have the equation of a circle with radius 5. They're asking me in part A to find the derivative with respect to x. However, even though a circle is simple enough that I can go ahead and find one expression in terms of x for the upper semicircle and the lower semicircle, and then to differentiate, I will avoid that process. I want to be able to find y prime or dy by dx without the need of having the separate expressions. And that can be achieved through implicit differentiation, which is what I want to show you right now. I will take the given relation, x squared plus y squared equals to 25, and I will take the derivative of both sides. The derivative with respect to x of the left side and the derivative with respect to x of the right side. And this is usually the initial process of implicit differentiation. You will differentiate the left and the right side with respect to x. Then every single term on the left will be differentiated with respect to x. So d by dx of x squared plus d by dx of y squared equals the derivative of a constant is equal to 0. So then this particular derivative, because I have d by dx of x squared, that will simply be 2x. Plus, now here, look at this term right here. I am finding the derivative with respect to x of y squared. What is important to remember here is that y by itself is a function in terms of x. So you do have here a composite function. What you have, let me guide you to this over here. What we have is that y squared is equal to f of x, some mysterious f of x, whose expression we don't know, with power 2. So we do have a beautiful composite function, meaning that we have to use the chain rule. So then we're going to bring 2 down using power rule. Then we're going to have y, subtracting 1 from 2, that will just give us y. But then we have to remember that we have to multiply by the derivative of y with respect to x. So we have to have times dy by dx equals to 0. And now what I'm going to do is to isolate the second term. I'm going to bring 2x to the other side. We're going to go ahead and divide both sides by 2y, that will cancel the coefficients. And the same thing over here. And we're going to have that dy by dx is equal to negative x over y. So all of a sudden, we have found the derivative of y with respect to x is equal to negative x over y. So some of the differences here when doing implicit differentiation is that your derivative may now have the two variables, x and y. And this is why we're going to go ahead now and use the point that we were given in part B to find the actual value of the slope so that we can find the equation of the tangent line. So that's the idea here. And this is why we end up getting x and y within the expression of the derivative. So continuing in this direction. Now the goal is to find an equation of the tangent to the circle at the point 3, 4, keeping in mind this is my x and this is y. So then I want dy by dx at the point 3, 4. That's going to be equal to negative 4 divided, I think that's not right. That's going to be equal to negative 3 divided by 4. So simple computation. And now to find the equation, we're going to have y minus 4 using point slope form equals to negative 3/4 times x minus 3. And it is now an easy task to find the actual equation. It's just by cleaning things up, isolating y, and simplifying the right side. So at the end, y becomes negative 3/4 x plus 25 divided by 4. And that becomes the equation of the tangent line at the point 3, 4. Now here, we are bringing back the same relation that we discussed a few minutes ago that gave us the graph of this curve that looks like a little loop or like a fish. I don't know. And we're being asked to find y prime. And if you remember, with a circle, we could still find two separate equations in terms of x. But with a loop like this, we have no expressions for those three equations. The best that we can do right now is somehow to try to work with the relation that they gave us at first. And again, I'm going to use implicit differentiation. So in order to do A, we're going to have x to the third plus y to the third equals 6xy. If you remember, to differentiate implicitly means that we're going to take the derivative of the left side and the derivative of the right side. And another thing that I want you to keep in mind is that every time that you see this y right here, you have to remember that y is a function in terms of x, only that we don't know what that equation is. What are the expression for the f of x's? We don't know that. So we don't know what f of x is equal to in a particular piece of the curve. We just know that it's some function in terms of x. So taking the derivative, I'm going to have d by dx of x to the third plus d by dx of y to the third equals d by dx of 6xy. So that's what I have. Then differentiating on the left side, we're going to have 3x squared plus 3y squared times y prime. Here I'm using chain rule, equals 2. And then I'm going to use, look at this over here. I actually have a product of two functions. One function is just x, and the other function is, again, this y right here with its own expression that we don't know, unknown, but it's a function. And I have a product of two functions. So I'm going to use product rule. I'm going to somehow leave this 6 alone, and now I will apply the product rule. The derivative of x is just 1 times y plus x times the derivative of y will just be y prime. Then we're going to have 3x squared plus 3y squared times y prime equals to 6y plus 6x times y prime. Now the goal is to take all of the terms with y prime and to collect them on one side of the equal sign. And everything else, for example, this guy over here, will go to the other side. So we will have 3y squared times y prime minus 6xy prime equals to 6y minus 3x squared. Now, we're going to go ahead and factor y prime out. So that will give us y times 3y squared minus 6x equals to 6y minus 3x squared. And then the next step will be to isolate y prime by dividing by 3y squared minus 6x, 3y squared minus 6x. This factor will cancel here, and we will now have that y prime is going to be equal to 6y minus 3x squared divided by 3y squared minus 6x. We can clean things up a little bit. For example, I can go ahead and factor a 3. So that will give us 3y minus x squared divided by 3y squared minus 2x. The 3's are going to cancel, and then we can have a little bit of a more simplified expression for that derivative. Okay, so this becomes the derivative. And again, notice what happens whenever we differentiate implicitly. What happens is that our expression for that derivative has the two variables in there, x and y, because we're going to have to now take both coordinates of the given point and substitute them into the expression to be able to find the slope of the tangent line. And you can see the tangent line right here at the point 3, 3. All right, so find the tangent to the curve at the point is part B. Let me move all the way up here to gain a bit of space. And let me use black instead. Okay, so then if I want to find y prime, all that I have to do is to plug in the x value and the y value. Remember the point, this is x and this is y. That means that we're going to have 2 times 3 minus 3 squared divided by 3 squared minus 2 times 3. That will give us 6 minus 9 divided by 9 minus 6. And when you simplify that, you end up getting that y prime is equal to -1. And that becomes the slope of the tangent line. Okay, so this particular line will have a slope of -1. And then part C is now asking, well, at what points in the first quadrant is the tangent line horizontal? So horizontal implies that y prime has to be equal to 0. So I take the expression that I just obtained for y prime, and we set that equal to 0, and then we can easily cross multiply. So when we do that, we end up getting 2y minus x squared equal to 0. We can easily solve for y, and we get that y is equal to x squared divided by 2. So then, with that in mind, we're now going to go ahead and substitute this expression right here into the original equation that we were given to find all the values of x where the derivative will be equal to 0. Substituting, we're going to have x to the third plus x squared over 2 to the third equals to 6x times x squared over 2. That will give us an expression that looks like this. 8x to the third plus x to the 6 equals to 24x to the third. I skipped a few steps in that process to save on time. And then bringing everything to one side, we're going to have 16x to the third minus x to the 6. And then we're going to go ahead and factor x to the third out. So this is going to give us 16 minus x to the third times x to the third. And continue simplifying. That means two things, that x to the third is equal to 0, or that 16 minus x to the third is equal to 0, in which case x will be equal to the cube root of 16. But instead of simplifying the radical, I will express this in exponent form, as in power form. So that's going to be 2 to the 4/3 whenever you simplify that. Now, from here, we get that x is equal to 0, but because we want to be in the first quadrant, we will just go ahead and focus on this solution that we got here, that x equals 2 to the 4/3. And now in order to find the y value, then we know that y is equal to x squared divided by 2. So doing a simple substitution will give us 2 to the 4/3, all of it squared divided by 2. When we simplify, again, skipping a few steps, we're going to get 2 to the 5/3. So therefore, the conclusion is that the slope of the tangent line is going to be horizontal in the first quadrant at one particular point. The point with x coordinates 2 to the 4/3 and y coordinate 2 to the 5/3. This is the last question with two parts, and all that I want to do here is just to have fun differentiating implicitly. We're not going to be finding horizontal slopes of horizontal lines or anything like that. We're just going to go ahead and differentiate, find y prime, and stop there. All right, so on the left, we're going to take the derivative of every single part. So then d by dx of y to the 5th plus, I'm going to bring the numerical coefficient, place it in front right away, and then d by dx of x squared plus, not plus, excuse me, that will be times y squared plus 5 times d by dx of x to the 4th equals to d by dx of the constant term on the right side. Now, keep in mind that here, I'm going to go ahead and use the product rule. Here, we're going to use chain rule. And here, just power rule. Same thing over here. The derivative of a constant is 0. Differentiating 5y to the 4th times y prime plus 3 times, using product rule, we're going to have 2x y squared plus, then we're going to have here x squared times 2y times y prime plus 20x to the 3rd equals to 0. Simplifying, 5y to the 4th times y prime plus 6xy squared, and then plus 6x squared y times y prime plus 20x to the 3rd equals to 0. And just as before, I will now collect all of the terms with y prime, and then the other terms right here, they're going to go to the other side. So on one side, the terms with y prime, and then on the other side, everything else. That means that we're going to have 5y to the 4th times y prime plus 6x squared y prime equals negative 20 x to the 3rd minus 6xy squared. We're going to factor y prime out, and that's going to give us 5y to the fourth plus 6x squared y equals to negative 20x to the third minus 6xy squared. And then dividing, we're going to have the same numerator, or the same expression as the numerator, divided by the factor on the left, 5y to the fourth plus 6x squared y. Okay. And then this becomes the expression for the derivative. If we wanted to find the slope of a tangent line at a specific point, then as long as we know the coordinates of the point, we can substitute them into the expression and we have the slope of that line. In this case, we begin again differentiating implicitly. If you notice, it is just impossible for me to solve for y. Just like in the previous problem in part A. In part A, the expression was so complicated that it was impossible to solve for y. Same thing over here. I cannot do that. So then I'm going to go ahead and differentiate implicitly. On the left, if you notice here, we're going to use the chain rule. But then again, y is a function in terms of x. And over here also, y is a function in terms of x. So then we're going to have the derivative of sine is cosine of x plus y. And then using the chain rule, the derivative of x is 1 plus the derivative of y is just y prime. That's going to be equal to, now over here on the right, we're going to use product rule because we have y squared times cosine of x. So the derivative of y squared will be 2y times y prime times cosine of x plus y squared times derivative of cosine of x minus sine x. And then now simplifying, I will substitute the, I will distribute cosine of x plus y nicely. So we're going to have cosine of x plus y times 1 is the same thing. And then plus cosine of x plus y times y prime. That's going to be equal to 2y y prime times the cosine of x minus y squared times sine x. And here is one of the terms with y prime. Here is the other one. So I'm going to group them. The y primes on the left, everything else on the right. So cosine of x plus y times y prime minus 2y y prime cosine of x equals to negative y squared times the sine of x minus cosine of x plus y. Factoring y prime out will give us cosine of x plus y minus 2y cosine of x equals to negative y squared sine x minus cosine x plus y. Whoa, okay, now finally y prime will be the entire expression on the right side. That will now form my numerator, and then the factor on the left side will form my denominator. Okay, and that becomes the expression of my derivative. If I could actually simplify, have some sort of cancellation going on, I would do that. But in this case, I don't even want to try expanding using identities or anything at all. This is good enough as a final expression.